So, welcome to module number two, where we are going to begin talking about the Boolean connectives and how they're related to truth values. This is tied back to chapter three of the textbook, so don't forget to read through chapter three before watching the video. So, our main learning objectives for this particular module are to first construct complex sentences using the three simplest connectives. And we'll introduce the notion of conjunction, disjunction, and negation. And then we'll start the process of using truth tables to determine the truth value of complex sentences that have been constructed from these connectives and the various atomic sentences. And I say we'll start that process because in our next module, we'll talk in detail about truth tables. And here we'll just sort of mainly be introducing them. We'll also offer a slight variation on the semantics of these statements. And we'll be looking at the game semantics that's offered in the textbook as well, as another means to sort of understanding when a given sentence is either true or false. And then finally, we'll be talking a lot about sort of translating between English and these first order sentences and what that looks like for conjunction, disjunction, and negation. And in regular old English, there's a lot of ways that we have for saying something like a conjunction or a disjunction. So we'll say a bit about that. And then at the end, we'll talk a bit about some alternative notation that we could have used, Polish notation and prefix notation as well, and that'll be important for understanding the discussion for this module. So later we'll be introducing some more truth functional connectives, but for now we'll stick to the three most basic Boolean connectives, and they are ones that have a nice English counterpart in our everyday language. And all the connectives that we'll look at, the Boolean connectives, are what are called truth functional connectives. And the book goes into a little more detail, and I've included that quote here. It says that the truth value of a complex sentence built up using truth functional connectives like this conjunction, disjunction, and negation depend on nothing more than the truth values of the atomic sentences from which it is built up. And what that means is that we'll build up these more complex sentences in a recursive fashion, much the same way that we built terms from function symbols. And as we build up those more and more complicated complex sentences, the truth value of those complex sentences really only depends on the truth values of the atomic sentences sort of down below. And so we'll say a bit more about that. But we have conjunction, and it's represented by this symbol that looks like maybe an upside down V. We'll call it the conjunction symbol. And in the English counterpart, when you're sort of saying a sentence in English, the counterpart would be a connective like and. So if you use the word and in a sentence, that would be a conjunction. The disjunction is denoted by this V symbol here. We'll again call it the disjunction symbol. And its English counterpart is that of the statement or. So you can combine two sentences in English with an or like this. And then finally, the last is negation. It looks almost like maybe an L that's sort of been turned sideways. And the negation is supposed to represent in sort of everyday English, it is not the case that. So it sort of switches the truth value of the particular statement. But these will be the three main connectives that we look at in this particular chapter. These are not all of the truth functional connectives. We'll tell the complete story about all of them. And for now, we want to just focus on building up complex sentences from these three connectives. So let's begin with the negation symbol. And when we are building up complex symbols with the negation symbol, we do it in an iterative or recursive process. So what we can do is what's sort of stated in that first bullet up there in gray if we have a sentence, for example, an atomic sentence, right? So if we were just back in our previous chapter, back in module number 1, the only thing we could really state, and the simplest things we can state, are atomic sentences. If we have a sentence or something like an atomic sentence, then we can put this negation symbol out in front of that atomic sentence, and we obtain another sentence. In this case, it's not an atomic sentence any longer, but it is a complex sentence. And we can then use that sentence again in this definition. So, for example, negation P is a sentence, and so we could put another negation symbol out in the front. So we could have negation P as well, and so on and so forth. So anytime you have a sentence, it's always possible to place a negation sitting out in the front, and you obtain, again, another sentence. And notice this is similar to the sort of predicate notation that we were using for a one-array predicate here. But again, this is not going to be a predicate. It's a truth value connective. Before I go on to sort of discussing the truth values of this particular connective and how they're defined, let's say a bit about that third bullet point there and what we mean by a literal. So as I said before, an atomic sentence is a sentence, and so we can put a negation symbol out in front of an atomic sentence. And if we have an atomic sentence that's been negated, we call that a literal. And so we'll be referring to that sort of definition later on in this video, and then also throughout the semester as well. So a literal is just the negation of an atomic sentence. Now, you can also negate complex sentences as well, and those won't necessarily be literals. But if you've negated an atomic sentence, that's what you'll call a literal. Now, just as a reminder, every first-order language has the equality predicate as one of its predicates. And if we were to negate some atomic sentence that was using the equality predicate, then we would sort of write it with the equality line with a slash through it, right? So this is sort of typical in mathematics. When you say that two things are not equal, you write sort of a slash through them. So in that case, those would be examples of literals. Now, this is a truth functional connective. And what's meant by that is that the truth value of this new sentence, negation P, is completely determined by the truth value of sort of the underlying sentence P. And if we follow that iterative process down further and further, looking at more and more applications, then it'll end up just depending on the truth values of those atomic sentences, right? And if we're in something like Tarski's world, the truth value of those atomic sentences depends on the world that you've constructed. And the truth values may change depending on the various shapes and the names that you've given to those shapes in Tarski's world. Now, what we'll say is that the way we define the negation of P is with this second bullet point. That sentence, negation P, is true exactly when P is not true. So in other words, it just sort of flips the truth value. And that information is given in a table down at the bottom of this sort of grayed out piece. On one column there, you have P, and below it, you have true and false. And so if you have a sentence, that sentence will either be true or false. And so those are the two possibilities for that sentence P. And that's enough information to then determine the truth value of negation P. And you don't even need to know what P means, just whether or not P was true or false. And again, that's what's meant by a truth functional connective. It's really only determined, its truth value is only determined by these underlying sort of atomic sentences or this recursive process. And again, the negation sort of flips around. So if P is true, the negation of P is false. And if P were false, the negation of P was false. Okay, we'll also talk a bit about some game semantics as well. So there's also another method for talking about game semantics. And what you're seeing here is our first example of a truth table. And we'll see those coming up again in our next chapter as we start to talk about tautological consequence and that sort of stuff. The next logical symbol, truth functional connective that we'd like to introduce is conjunction. Again, conjunction is represented by this upside down V symbol. And again, it's a recursive definition. This time, the conjunction is a lot like a two-arity predicate, and so it'll need two sentences as its input. So if P and Q are sentences that we've already constructed, either atomic sentences or complex sentences, then we can form a new sentence by writing down P, the conjunction symbol, and then Q. And we read that as P and Q, or P conjunction Q. And that then produces a more complex sentence. And that sentence can, again, then be fed back into that bullet point number one and repeatedly applied, right? So as we produce more sentences, we get more and more sentences. And this is a lot like what happened, again, with our function symbols and our complex terms. And then here, the truth values are determined in the following way. The conjunction of P and Q is true exactly when both P and Q are true, and no other possibility. So for example, on that table down there, we've got P and Q, and now instead of having just two rows, we've got four, because there are four possibilities. P and Q could both be true, and the second and third column, one is true and the other is false, and then in that last row down there, both P and Q are false. And the only way that the conjunction is true is if both P and Q are true. So that top right sort of corner there is marked as true, and everything else below it is marked as false. So that bullet point number two, all that information is given directly in terms of that truth table for conjunction. And again, notice that the truth value of the conjunction doesn't depend on sort of the meaning of P and Q, just on whether or not P or Q are true or false. And because this is sort of this recursive process, we can go all the way down to those atomic sentences and sort of check to see if the atomic sentences are true or false. And that'll lead to whether or not the complex sentence is actually true or false. Again, we'll also have some semantics for this in terms of the game semantics as well. If you've already read the textbook, you maybe have read a bit about the game that you can play in Tarski's world. But that's also another excellent way to determine the truth values and give meaning to these complex sentences built from these truth value connectives. Our final connective from this module will be the disjunction symbol, represented with sort of this V-looking symbol there, which I'll call the disjunction symbol. And again, it's a recursive definition. If you provide me with two sentences, P and Q, they can be atomic sentences or complex sentences, then you can form a new sentence by writing down that sentence P, writing down the disjunction symbol, and then writing the sentence Q down. And that new expression that you've written down will, again, be a sentence, and you can feed it back into this definition and into the previous two definitions as well. You can start using it in the definition from conjunction in negation. As well, building up more and more complicated terms. And again, as we do that process, the truth value of these complex sentences that we produce is really determined by the underlying truth values of the disjuncts, the P and the Q. And again, if we follow that all the way down to the atomic sentences, it's really just sort of based on whether or not the various atomic sentences are true or false. Here, the semantics are given in the following way. So again, that's the meaning of these sentences, whether or not these sentences are true or false. The sentence P or Q, in this case, P disjunct Q is true, provided that P is true or Q is true. And then in parentheses here, just be a bit careful. It could also be the case that both of them are true. There's also something called the exclusive or, which gets marked as a false if both P and Q are true. But here, when we refer to the disjunction symbol, we are allowing for the possibility that both P and Q are true. And so you can see that information here in the truth table. Again, we have 4 rows for the various truth values of P and Q. And if one or both of P and Q are true, then you write a true there. And the only time you get a false in that final column there for the disjunction is if both P is false and Q is false. And this tells you everything you need to know about determining whether or not one of these complex sentences that's used a disjunction symbol is either true or false. And again, It's only dependent on whether or not P or Q are false, and not really about their meaning so much. Again, that's what's meant by this truth functional connective. Now, you can start seeing how many different possible truth functional connectives there are, because there's only a finite number of ways to fill out these sort of truth tables down here. And in the next couple of chapters, we'll start discussing other types of connectives and the fact that some of them are basically redundant. So here is an important remark from the textbook and a convention that we'll adopt. It's not adopted by all textbooks on logic. In some instances, anytime you use these conjunction symbols or disjunction symbols, some textbooks will ask that you put parentheses to indicate where the scope started and basically where it ends. And if we were being really precise, then we would do that. However, in order to be sort of economical with our expressions and make things a little more readable and easy to present, we'll follow the following convention here, that parentheses must be used whenever ambiguity would result from their omission, and only then, right? So if you can omit some parentheses and there's no ambiguity in the meaning of the sentence, then that's perfectly fine. And so that's why you've seen in our previous 3 rules that we've omitted those parentheses. But we should be careful to include them anytime that it might be unclear what the meaning of the particular complex sentence is. And what I mean by that is, if there's any question about maybe an order of operations, what's sort of coming first or what's coming second and that sort of thing, instead of giving some priority like you would back for multiplication and addition and that sort of thing, we'll just put in some parentheses to make sure to sort of clarify everything. Now, one interesting thing that we'll see at the end of the video and also in the discussion for this module is that there are some interesting prefix notations that we can follow, similar to what we used for our atomic sentences and complex terms, where we can just avoid parentheses altogether. So if we're being really economical with our symbols, we can use that notation. It's called Polish notation and prefix notation, and we'll say a little bit about it. I'll just say that the reading of those particular expressions then becomes very difficult to read. So we can omit the parentheses, but then it's hard to read. So we sort of follow a mix of both, right? So that makes the expressions sort of easier to read, and then also sort of minimizing the amount of parentheses and that sort of stuff. Okay, so in this chapter, the semantics of our complex sentences are described in 2 ways. One is with truth tables, and we've already seen that with our Boolean connectives. And we'll see more complicated truth tables coming up in the next module and also the next chapter. But there's also an alternative method to understand the semantics of our complex sentences. And what I mean by semantics here is, their truth values, right? Is the sentence that you've written down either true or false, and here that gives us the meaning of our particular sentence. And as we've said before, the key feature of our Boolean connectives is that they're truth functional. In other words, the truth value of the complex sentence relies only on the truth conditions of the underlying atomic sentences used in the construction of that particular complex sentence. And this is really underscored quite well by a nice game that was introduced by 2 logicians, Henkin and Hentika. And there's a nice implementation of this particular game within Tarski's world. Now, the game is a 2-player game. You have 2 players, let's call them, say, Max and Claire, and they disagree about the truth value of some complex sentence. So there's some complex sentence in the first order language, and one of them, let's say Max, thinks that it's true, and the other, Claire, thinks that it's false. And if they were in agreement about this, then there would be no need to play the game. But so one thinks it's true, the other thinks it's false. And this game is played in a series of challenges. So they go back and forth challenging one another to justify their particular claim. But they do that justification in terms of simpler claims and simpler sentences. And what I mean by simpler is that they'll reduce the initial complex sentence to a sort of complex sentence that has less Boolean connectives in it. And if you repeat this process over and over, removing those Boolean connectives. Eventually, at some point, there are no Boolean connectives, and you get down to atomic sentences. And then at that point, you can just inspect the atomic sentences and see, are the sentences actually true or false? And that will then tell you if your initial commitment was either true or false. Now, when you play this game in Tarski's world, and on the next slide, we'll actually go through some game plays of it, and in the homework, you'll be asked to do that as well. Tarski's world will take the role of one player, and you'll take the role of the other. And so there'll be some complex sentence written in Tarski's world. And when you play this game, the first thing that the game will ask you to do is to specify your commitment. Do you believe the sentence is either true, or do you believe the sentence is false? Now, if you believe the sentence is true and you're dealing with something that was built in its last step using this disjunction symbol, so that top row there, then it's your turn to move, so you'll be the player. And your goal will be to pick the simpler sentence, either P or Q, that you think is actually true, right? So if you think that that sentence P or Q is true, then you think one of P or Q is actually true, possibly both. And your goal at this stage will be to then present P or Q. And notice that that has one less conjunction symbol, and then you repeat the whole process again, right? And then you go through this sort of thing. And again, you're sort of now saying that that simpler claim is true. Now, if you initially committed to it being false, then the first move would be given to Tarski's world. And what it will do is it'll say, okay, so you think that statement is false. And it'll say, oh, okay, all of the things there, P and Q, are both false. And so it'll go through and try and find one that it thinks is true. And it knows how to evaluate things, using the evaluation tool. And so if there is one that is true, it'll go through and actually pick that one out, right? And that's a simpler claim, and then it thinks that that's the true one. And so you are still committed to that claim being false, and you continue the process. And then the conjunction is essentially the same sort of setup here, except for if you believe the statement is false, well, then you have to pick one of the two simpler statements, either P or Q, which is false. Okay, so then you're now tasked with picking the false one. And if you believe the conjunction is true of P and Q, it's Tarski's world's turn, and it'll be tasked essentially with trying to choose the one that is false. And then the easiest is sort of negation. It doesn't matter what your commitment is, you just simply replace that negation P with P, and then you switch your commitments, right? So the two players switch their various commitments. And again, the goal here allows us to step down to a simpler sentence. And by simpler, again, I mean less Boolean connectives. And so after a finite number of steps, there won't be any, and you're down to atomic sentences. Okay, so these are sort of the game semantics. And again, they really underscore the truth functional nature of the Boolean connectives. Again, on the next slide, we'll go through an actual example using Tarski's world. Okay, so here I've loaded Tarski's world with a world file where we've got 3 blocks, A, B, and C, that are all cubes, with C being the largest, A being sort of in between, and then, B being in between, and then A being the smallest. And then I've also introduced 3 complex sentences, the first being built from disjunction, the second conjunction, and the last negation. And we'll go through and play an example of the game. So this is the complex sentence that I'll have a disagreement with Tarski's world with. And we'll go through and try and hash it out, breaking it down to the atomic sentences to figure out if this statement is either true or false. And this is particularly useful when you have fairly complicated sentences, and sometimes in a homework assignment, you may open something up, try to evaluate it, and you'll see that maybe it looks sort of difficult to parse, and it's not clear if it's true or false. You can always play the game, and it'll help you sort of break down the complex sentence so you can better understand how the truth values are related to the underlying atomic sentences. Okay, so let's come up here. We're in that first sentence. And the first thing it will ask me to do is to pick my commitment, either true or false. Typically, you should pick what you believe to be the case. In this case, I think this is a true statement, so I'll hit true. Now, Tarski's world tells me, so you believe the statement is true, and it'll take the opposite commitment. It now believes the statement is false, and we'll go back and forth trying to justify our claims until we get down to an atomic sentence. And in this case, it's just going to be basically in one step, because now it says, all right, well, the only way that you're going to believe that this disjunction is actually true is if one of the disjuncts is actually true. So in other words, either smaller AB, smaller CB, or smaller BC, one of those has to be true. And so it challenges me to then say which of those is true. And notice those are actually simpler sentences because they no longer have any Boolean connectives in them. In fact, they're atomic sentences. Okay, so now I'm prompted to pick it out. So this is my choice now. And if I'm trying to justify my claim, I'm actually going to try and pick out the one that is true. And so, or at least one that is true. Maybe all of them are true. But here it looks like smaller AB is actually true. So I'm going to pick that one as my commitment. And then Tarski's word will come back and says, okay, so you believe that's the true one. And I say, yeah, that's right. And it says, okay, then you're the winner of the game. You've correctly justified this particular statement, and your original commitment about the complex sentence was correct. So that's true. Now be a bit careful. You can sometimes make the wrong choice. And even if you have the right commitment and the right truth value from the very beginning, you can also lose the game. So if I were to pick to the second atomic sentence, smaller CB, you'll notice that C is actually bigger than B here. So that atomic sentence is really false, but I'm going to sort of say, oh, that's the one that I picked. If I do that and it says, so you believe that statement's true, I'll say, yeah, I think so. And it then says, oh, well, you're the loser then, because in fact, that statement was false, and false was the commitment that Tarski's world was taking on. So it's now justified its sort of sequence, and you lose. So be a bit careful here. You can have the right commitment, and even if you lose, it doesn't mean that the statement is false. Okay, and then just this smaller BC one down here, that one is true, so here we would also win the game as well. But let's come all the way back to the original commitment and now commit to the opposite. So let's say we thought that this disjunction was false. And the only way a disjunction like this will be false is if each one of the disjuncts turns out to be false. In other words, Tarski's world is going to come back and say, you believe all of these are false, right? And it thinks the opposite. It thinks that they're actually true because it's taking on the opposite commitment as you. And so it's then tasked with having to go through at this stage of the game and pick out the one that really is true. Now, if there is a statement that's true, it'll pick the right statement. But sometimes there's not a statement that's true, in which case you'll be able to win the game. However, in this case, it picks out that true statement, smaller AB, as being the one that it thinks is true. And so it thinks, it tells me, you think it's false, right? And I say, okay. So in this case, I've now lost the game because, in fact, it really is the case that smaller AB was true. And that's the statement that Tarski's world picked. But again, hopefully you're sort of noticing here that we're taking our complex sentence and reducing it down to something simpler and eventually, in this case, in one step, down to an atomic sentence. And so the truth value of that complex sentence is based on those atomic sentences. Again, that's that truth functional component. Okay, so let's end the game and move on to the conjunction here. And play this. So in this case, things are a little bit different. So let's start out saying perhaps that this is a false statement. It's not false, but let's go through and play with the commitment to it being a false statement. And if a conjunction is false, right? If a conjunction is false, what that means is that at least one of these formulas has to be false. And so this is sort of like a dual game to the one for disjunction. Instead of choosing the true statement, you have to now choose the false statement. So it's asking you to then say, okay, well, which one of them is the false one. And in this case, there's no way I can justify my claim because cube A, cube B, and cube C are all true. So if I pick any one of them and say that was my commitment to being false, it's going to tell me that I'm a loser because cube A is actually true. Okay, so that's how the false sort of commitment works for the conjunction. And the true works the way that false did for disjunction. So let's now pick that true. So it says, okay, you believe that this conjunction is true. That means that you believe all of those formulas are true. And now Tarski's world believes that the statement is false, and its task is to then go through and actually pick out the false one. And if there is a false one, it'll pick it, right? But in this case, it can't do that. And so it just picks cube A, that very first one, the same sort of thing I did. And then it says, oh, you win because cube A is actually true. And I've justified my initial commitment, and the statement is actually true. The simplest of the games are the ones associated to negations. Let me just run that one really quickly. What happens is you just sort of swap your assertion and remove the negation symbol. So if I were to say, I believe that negation tet A, so it is not the case that A is a tetrahedron, is true, well, then it'll say, okay, you believe that statement is true. And then it says, so you believe the opposite, the one without the negation is false. And it'll say, yeah, that's what I believe. And then notice that that's an atomic sentence. And I've won the game because this tet A actually is false. And so my original commitment has now been justified, and that statement actually is a true statement. Let's now go back and just see what happens if we pick the wrong assertion here. So let's say this was false. Now it's going to tell me that you believe that tet A is true, and that's again because it removes the negation and just flips the commitments. And then it says, okay, well, you are a loser because tet A is actually false and not true in this world. Okay, so those are the three, and again, they're sort of giving you a rationale for why we're getting true in these three cases here for this particular world. Okay, so now that we've seen the game, let's now switch gears a little bit and introduce the notion of what we mean by logically equivalent sentences. And in this case, two sentences turn out to be logically equivalent if they have precisely the same truth values in every possible circumstance. Now, in the next couple of slides, I'll give you some really concrete logical equivalences in first order logic. But I am also bringing this slide up because this is also the criteria that will judge our English translations by. So one of our learning objectives has been to sort of translate back and forth from colloquial English back into first order logic and vice versa. And we found that going from the first order logic, the precise statement, back to English can be pretty sort of straightforward. You just write out the interpretation. But going the other way around can be tough because there's often a lot of things that we can use in English that just don't appear in our first order language or can't be conveyed by our first order language. And the point of bringing that up is that when you do write down sort of an English translation, so just into everyday regular sort of English, the only criteria that you'll be judged by on whether or not that's correct is if it's logically equivalent to the sentence that you were given, right? So that first order sentence that you were given. Not on the style of the sentence or the prose of the sentence or any of the other sort of implications that could come along with that particular sentence. Simply that it's logically equivalent. So, I mean, it could even essentially be a run-on sentence or something like this, as long as it's an actual sentence and it has the same truth value That's what makes it a good English translation. Now, that's the only criteria I'll sort of judge you on. On the other hand, we'll see some sort of nice style variants and things like that that can help you make it look a little bit nicer and sound a little bit better than just sort of dryly going back through and writing out and for every conjunction and or for every disjunction. Okay, so here are a handful of pretty straightforward logical equivalences. Here, that double arrow between the sentences indicates logical equivalence. And again, logical equivalence meaning that the two sentences have the same truth values in all possible circumstances. So let's focus in on that first one. It says that the double negation of a sentence is logically equivalent to the original sentence itself. And this is pretty straightforward to see. Remember that from our truth table for the negation, what it does is it just sort of swaps the truth values. So true becomes false and false becomes true. And if we do that 2 times in a row, we get back to the same truth values. And so those two are logically equivalent to one another. And in the English language, we try to avoid these sort of double negatives typically, although sometimes they are used to emphasize sort of the negativity, and they don't actually cancel out in the English language. But here in first order logic, we'll use them, and they'll often show up in even things like, a triple or quadruple negation or something like that. Might even pop in from time to time. Okay, so that's double negation. And again, it just follows directly from that truth table definition of the negation. The other 2 laws that you're seeing here are De Morgan's laws for conjunction and disjunction. And they give a really nice connection between disjunction and conjunction. So let's focus in on that second one. The left-hand side of that logical equivalence is the negation of the conjunction of P and Q. Now, the only way that sort of sentence is going to be true, right, is if the conjunction is actually false. So P and Q is false. And if P and Q happens to be false, that means that either P is false or Q is false. And that's what you're seeing on the right-hand side. And this is really part of that game semantics that we saw in Tarski's world, where if we were looking at a conjunction of terms and we thought that it was false, then we had to commit to which of the pieces we thought was false. Whereas if we were looking at a disjunction and we thought it was true, then we had to commit to which of the disjuncts was true. But really, that rule that we were using in the semantics there, in the game semantics, was this De Morgan's law. And likewise, for number 3 there, if the disjunct happens to be false, right, negation of P or Q, if that disjunct happens to be false, the only way that it could possibly be false if both of the disjuncts were false. In other words, negation P and negation Q. And so these are just sort of obvious consequences directly from those truth tables and the meanings of those symbols. But there's a couple of things to point out with this sort of setup. First off is that in these logical equivalences, you'll notice that on one side, we have, for example, on that line 2, a negation and a conjunction, whereas on the other side, we have a negation and 2 negation symbols and a disjunction. And so it's a relationship between conjunction and disjunction. And on the next slide, I'll show this in a bit more detail. You can combine this with double negation to show that conjunction can be written in terms of disjunction and negation, and vice versa. Disjunction can be written completely in terms of conjunction in negation. And so I'm trying to point out here that we didn't really need to introduce both conjunction and disjunction. We could have got away with just introducing one and then sort of defining the other using one of these De Morgan laws. Or if we were trying to be very economical with our expressions, we could just avoid one or the other. And there are some instances where we'll want to do that sort of thing. But again, these are some really nice logical equivalences, and you're free to use them throughout the semester in your informal proofs. But in your formal proofs, you'll have to go through a bit more detail. So here is another logical equivalence. And there's actually two logical equivalences here because there's two of these double arrows. So there's actually three sentences floating around. And in this case, we've used double negation and De Morgan's law together. So let's start there on the left-hand side. So we've got P and Q, the conjunction of P and Q. And by double negation, that turns out to be logically equivalent to negation of the conjunction of P and Q. So that's what we have there in the middle. And again, that logical equivalence is justified by the double negation. And then what we can do is we can pass one of those negation symbols, that very first one, the one on the right, through the parentheses using De Morgan's law. And when we do that, what happens is the conjunction turns into a disjunction, and we get negations on the sentences P and Q. And so on that right-hand side, we've got this negation, and then our parentheses, another negation, P, disjunction, negation, Q, and then you have the closing parenthesis. And that sentence is logically equivalent to the conjunction of P and Q. And the point of this is just, as I said before, notice that that expression on the right-hand side doesn't have a conjunction in it at all. It only has disjunctions and negations. And so the conjunction, in some sense, is a bit redundant here. It could have just been defined in terms of disjunction and negation. And vice versa as well. The disjunction also is definable in terms of conjunction. Now, as we go on, we'll start introducing more Boolean connectives, and we'll try to tell the complete story of the what are all the truth functional connectives that we could consider. And these two together, the disjunction and negation, or also negation and conjunction, turn out to be complete in the sense that you can sort of build up all of the other ones using those formulas. And we'll see that in later chapters with some interesting homework assignments. So here I'm just summarizing a few of the details that were elaborated on in the textbook. And I think this particular section of the textbook is really well written, and it's definitely worth the read. So I'm not going to reiterate everything they say there, but I'll remind you of some of the important facts here, or some things that can be really useful. First off, often when we're writing down an English expression, if we use a conjunction, an and, we can sometimes suggest some sort of ordering of the events, like it happened in the morning and then at lunchtime and then in the evening and at night or something like this. And that's never the case in first order logic. So that's not something that you can sort of translate in. And if you wanted to add that sort of in, you'd have to add it in the form of maybe a predicate or an atomic sentence or something like that, modifying your actual language that you're using to express this sort of temporal ordering. So be careful with that. There are a lot of ways in English that we have to basically make a conjunction. And some common ones are but, however, yet, nonetheless, and moreover. They're all stylistic variants of the conjunction or of the word and. However, they're not necessarily truth functional connectives, so to speak, because they sometimes convey more information. And in the section, they talk a little bit about how what comes after a but is often supposed to be, thought of as maybe a surprise or something, out of the ordinary or something like this. So there's some suggestions that these words have in ordinary English that just can't be translated into first order logic. And anytime you see but, however, yet, nonetheless, and moreover, you should translate them as a conjunction or vice versa. That's a nice way to sort of vary up your translation. If you're coming back into English, you might be able to use something like this. Now, the next one is going to be important as we talk a bit about alternate notation and parentheses and some of the ambiguity that we had been mentioning previously. We use parentheses when something might be ambiguous. And here we'll use the English expressions either or, so the either part, and the expression both something and something else, so the both and, to sort of basically work like parentheses, telling you where sort of the conjunction starts off in the sentence or the disjunction starts off in the sentence. And if it wasn't there, it otherwise might be ambiguous as to what the meaning of the sentence is. Like it's not quite clear. So the either sort of puts in this nice parenthesis. And you really need that sort of parenthesis because the way that we write in English is to use these sort of conjunction and disjunction symbols in their infix notation. So we put the and sort of in the middle of the sentence. However, we'll see a bit about prefix notation here in a moment and Polish notation and alternate ways of expressing some of our first order sentences where parentheses don't matter and we won't have to worry about this sort of thing happening. So we'll see that. And then we'll also see it in the discussion for this particular module. So here I'm just summarizing a few of the details that were elaborated on in the textbook. And I think this particular section of the textbook is really well written and it's definitely worth the read. So I'm not going to reiterate everything they say there, but I'll remind you of some of the important facts here or some things that can be really useful. First off, often when we're writing down an English expression, if we use a conjunction, an and, we can sometimes suggest some sort of ordering of the events, like it happened in the morning and then at lunchtime and then the evening and at night or something like this. And that's never the case in first order logic. So that's not something that you can sort of translate in. And if you wanted to add that sort of in, you'd have to add it in the form of maybe a predicate or an atomic sentence or something like that, modifying your actual language that you're using to express this sort of temporal ordering. So be careful with that. There are a lot of ways in English that we have to basically make a conjunction. And some common ones are but, however, yet, nonetheless, and moreover. They're all stylistic variants of the conjunction or of the word and. However, they're not necessarily truth functional connectives, so to speak, because they sometimes convey more information. And in the section, they talk a little bit about how what comes after a but is often supposed to be, thought of as maybe a surprise or something, out of the ordinary or something like this. So there's some suggestions that these words have in ordinary English that just can't be translated into first order logic. And anytime you see but, however, yet, nonetheless, and moreover, you should translate them as a conjunction or vice versa. That's a nice way to sort of vary up your translation. If you're coming back into English, you might be able to use something like this. Now, the next one is going to be important as we talk a bit about alternate notation and parentheses and some of the ambiguity that we had been mentioning previously. We use parentheses when something might be ambiguous. And here we'll use the English expressions either or, so the either part, and the expression both something and something else, so the both and, to sort of basically work like parentheses, telling you where sort of the conjunction starts off in the sentence or the disjunction starts off in the sentence. And if it wasn't there, it otherwise might be ambiguous as to what the meaning of the sentence is. Like it's not quite clear. So the either sort of puts in this nice parenthesis. And you really need that sort of parenthesis because the way that we write in English is to use these sort of conjunction and disjunction symbols in their infix notation. So we put the and sort of in the middle of the sentence. However, we'll see a bit about prefix notation here in a moment, and Polish notation, and alternate ways of expressing some of our first order sentences where parentheses don't matter, and we won't have to worry about this sort of thing happening. So we'll see that. And then we'll also see it in the discussion for this particular module. So the textbook goes into a bit about alternative notation. And here we'll focus in on just prefix notation and then also Polish notation. But the book talks about other types of notation from programming and various other realms as well. But these ones are interesting in the sense of parentheses and a bit about ambiguity. Because if we follow the prefix notation and Polish notation, it turns out that we can basically write out our complex sentences without any parentheses at all. And furthermore, there's no ambiguity at all either. So how does it work? Well, instead of putting the conjunction or the disjunction symbol in between the two complex sentences, like we have been doing, so you can see here, we instead put the symbol at the beginning, much like we would have done with a predicate symbol when we were forming an atomic sentence. And you can sort of think about it, if you're putting it in this way, as this conjunction symbol as being a symbol that's a lot like a predicate, with its arity being 2. So once you write that symbol down, you should then expect to see 2 sentences coming after that. And we'll label those 2 sentences, in this case, P and Q. And there are really sort of nice algorithms that you can write down to show that you can actually determine if some sequence of symbols is really just 2 sentences written next to each other. And so then you can always determine if an expression like this is well formed. And again, notice that you don't need any parentheses at all. For the disjunct, you do the same thing. You put the disjunction out in the front, and then you write the 2 sentences down, P and Q. And we actually could have done this with our atomic sentences and our function symbols as well. However, we added parentheses and commas to make it a little more readable and easier to understand. But again, we could have also done that in that situation. Now, the cool thing about negation is it's already in prefix sort of notation. And the reason why is because it's really as if it were sort of like a predicate symbol of arity 1, right? So it only has one sort of input, in this case, one sentence. And we always put the negation out in the front. So it's already in that format. And that's why we never had any sort of problem with parentheses related to negation symbols. Okay, so that is a bit about prefix notation. And the nice thing, again, is that you can avoid parentheses at all. And in terms of, talking about economy of symbols, like if we're trying to use the least amount of symbols in our expressions, this is a really nice way to do that, right? Okay, so that's prefix notation. And then there's also Polish notation. And Polish notation essentially uses prefix notation with the difference that instead of using capital letters for sentences to represent sentences, they use lowercase letters. So instead of capital P and capital Q, they use lowercase p and lowercase q. They use prefix notation, but instead of these sort of strange symbols that we're introducing, conjunction, disjunction, and negation symbols, they just use capital letters from the alphabet. For the conjunction, they use capital K. For the disjunction, they use capital A. And for the negation, they use a capital N. And this is fairly standard in Polish mathematics. And, logic has the sort of a deep history in Poland. And a lot of interesting logic came out of there. But this is the notation that they would use. And in fact, that's how they teach it. And then there's also a final variation on all of this, which just helps with processing some of these sequences. You can also reverse this. So if you run these sequence of symbols just in the opposite direction, so for example here, instead of KPQ, you could write Q, P, and then the capital K, that would be that sequence written in reverse. That's called reverse Polish notation. And that also has a bit of advantages. And some calculators still allow you to put in computations in this reverse Polish notation. All right, so let's end this video with an example that'll help you with the discussion post. So here I'm going to take a few expressions in our first order language that use some of our Boolean connectives, and we're going to convert them into prefix notation. That'll be there highlighted in green. And then from there, we'll talk about the Polish notation that you're seeing down there in orange. Okay, so the sort of sentence that you're seeing at the top, or the logical equivalences that you're seeing at the top, are the ones that we mentioned before about how to represent conjunction in terms of negation and disjunction. And let's focus on the conjunction of P and Q. So again, you just put the conjunction symbol in the front and then write the two sentences in order, P, then Q. And so that's what you see on that second line down. And then essentially that's what's done also in that second one with the double negation there, because double negation is already in prefix notation. So you just replace what's on the inside of those parentheses with that conjunction and then PQ. And I could have really actually dropped off the parentheses, and I'm noticing I sort of made a mistake here, but that's okay. I wouldn't mark off any points if you added some parentheses for clarity, but they're unnecessary at this point. And then finally, that last one that you're seeing there, well, the first symbol that shows up is that negation. And then it's a disjunction of the two simpler sentences, negation P and negation Q. So you write that negation, disjunction, and then those two sentences. So negation P would be the first sentence, and then negation Q. Okay, and then to convert down there into orange, you just take any capital P's and write them as lowercase p's, any capital Q's and write them as lowercase q's. Any negation symbols, you write them as capital N's. Any conjunction symbols you write as a capital K. And then a disjunction symbol you write as a capital A. Okay, and we get this nice sort of formula down here that, I mean, if you look at it for a moment and you're not used to that sort of language, it's sort of basically unreadable. However, if you're used to this sort of Polish dialect, then it's just as easy to read as what you're seeing on the top.